Hi guys.
Hello.
Let people in the meeting here. Just letting people in the meeting here. Let's give it a second and then we'll start.
Okay.
Angled right. Good. All right. Okay, let's go ahead and talk. So we just as a reminder, if you guys saw the announcement that I posted up the other day, yesterday, that our test is on Monday. We won't have a lecture on Monday. Our test will start at 10 a.m. on Monday. Okay, so that's like when we would have normally had our class time. Okay, so we're not going to have a class on Monday because the test is going to start then, and it'll go for 24 hours, and so it'll end right before class on Tuesday. Okay, so keep that in mind. Test is on Monday, basically from 10 a.m. until 10 a.m. on Tuesday. So keep that in mind. Also, the homework will be due. I've changed it to be due on Monday night. Okay, so if you guys have any questions, I think today also we're going to do it kind of like we did yesterday, where after I finish chapter 9.3, which is not on the test, but which will be on, stuff from next week, then 9.3, which is like what we would have covered on Monday. So we're kind of swapping these lectures here. Let's see what else. So 9.3 won't be on the homework and it won't be on the test. We're going to do it today. At the end of class today, okay, we probably will have some time. If you guys want to ask questions on the homework, okay, I'm totally good with answering homework questions, stuff like that. And then, excuse me, and then I'll have office hours again today at 12:30. So if you guys have any other questions you want to ask before we break off for the weekend, feel free to ask away. All right. So let's, I think we can go ahead and get started. So today we're going to be talking about chapter 9.3. All right, so chapter 9.3. 9.3 is all about the F-test. This is a table in the back of your book, okay? I didn't scan it in and print it because it's like many pages, so there's like too many pages to actually scan it in. But you guys can take a look. It's table A.4 in our book. Okay, if you want to go ahead and take a look at that, you'll probably need it in order to answer questions about the F-test. I'm going to show a picture of it today when we work through some examples so you can kind of get a feeling for how we're working through the what does it mean and how we're supposed to do it. Okay, so let's talk about what is the F-test and like why we would do it. So the F-test basically is testing differences between two variances. Okay, so the big question is, well, we kind of did that when we did the chi-squared test, right? Where we did the sample variance and the population variance. Now be careful, the chi-squared test is looking at a single random variable and we're comparing the sample variance with the population variance, okay? The F-test is looking at, like, if we have two different populations, like random variable X and random variable Y. Okay, so if I have this, let's draw this out. So if I've got, I'm gonna really exaggerate this. So this is my, this should be symmetric. This is my mean for my random variable X. Okay, my mean for that. And I've got some kind of a standard deviation for this too. So if I look at, let's go, this should be symmetric. I'm not a really great artist. So this distance here is our standard deviation for our random variable X. Now, if I compare this with the random variable Y, so random variable X and random variable Y, sorry, you can't see that, have the same mean, okay, these two variables here. But let's draw this out. So let me see if I can get this just right. Okay, it's still a normal distribution, okay? These still are two normally distributed. You can see how their variances are going to be very different, right? This one has a much wider variance, okay, than this one does here, okay? So these are, and we would maybe set that up, like that would be our design specifications to have, wider variations, say, for example. So let's write down exactly. Now the F-test, okay, is going to be comparing the variance here with the variance of y. These are standard deviation markers, but the F-test compares the variances of two separate samples, okay? The chi-squared test compares within one sample the variance, the sample variance, and the population variance. Okay, so here I'm comparing the variances of these two samples. Okay, so let's write that down in words. So we've got the two-sample test. So in chapter 9.2, we did also a two-sample test. We were comparing the means together, mean for my distribution of x and mean for my distribution of y, right? My random variable of x, my random variable of y. Now, remember we made some assumptions when we did those things like, well, are the means equal or the means not equal to each other? The F-test is something that we actually have to do first before we compare those means together, because the F-test is going to tell us whether or not those variances are equal to each other statistically speaking. So two-sample test. So I also want to be able to, it's going to test differences in variability between, say, one population, sigma x squared, and another population, say that's a y, sigma y squared. Okay, so this is my random variable for x, my random variable for y, the variance for my x distribution and the variance for my y distribution. And we want to do this especially when mu sub x, mu sub y are not significantly different. Okay, so mu sub x and mu sub y, they're going to be forming a part of like some kind of a hypothesis, right? But I need to check their variances first so I can do some kind of, do I know whether to do case 1 or case 2? The variances are the same, the variances are not the same, okay? So, and these could be mu of x and mu of y, so I could have random variable. Right, these could have different sizes, right? I could have, 10 sample sizes here and 30 sample sizes here. The F-test is going to take into account these different degrees of freedom for each sample that we're working with. Okay, so just in a nutshell, right, what our F-test is trying to do, okay, comparing the variances between two separate populations of things, okay? And we want to do this first before we actually talk about testing the means of things. So if you guys are ready, I'm going to flip the page on here. Does anybody need more time to write what I've got written down here? So we set up, talk about our hypotheses. Right, so our hypothesis, so in the past we've been talking about checking the mean, right? So I want to be able to check, is this mean equal to a value? Are these two means equal to each other? Okay, so here we're going to be checking our hypothesis. Our null hypothesis is going to be sigma x squared is equal to sigma y squared. So our population variances are equal to each other. Okay, that's our null hypothesis, right? So what we want to do is we want to be able to reject our null hypothesis when, okay, we're going to reject our null hypothesis in our right-tailed, left-tailed, and two-tailed case. So let's talk about those three different cases, right? So in terms of our right-tailed case, okay, so this is going to happen when we have an alternative hypothesis, when we say sigma x squared is greater than sigma y squared, okay? So, right, this is right-tailed, right? This variance here is greater than that variance, okay? That's our alternative hypothesis. It's going to look like this. Okay, I've got some kind of a thing that's happening here, okay? This is coming from our F-test. We're going to talk about the F distribution in a minute and what it looks like. Okay, so what we do is we say, let's see, so I want to actually talk about, okay, so I'm actually giving you what these things look like without actually telling you this is from the F distribution, but I haven't actually told you what the F distribution is yet. So give me a minute. Let me draw out what these pictures look like and what our alternative hypothesis is, and then we're going to go into details about our F distribution, okay, and the criteria here for making that decision. Okay, so the right-tailed, okay, our left-tailed. Okay, our alternative hypothesis is going to look like squared is less than sigma y squared. It's going to be something like, these are all based on some alpha level that we're working with, right? We're given some kind of alpha level. And then our two-tailed. Okay. This is our F distribution here. I'm intentionally drawing this slightly asymmetric, okay, because our F distribution actually is asymmetric. Okay, so we're talking about variances here. So be careful, if you're given standard deviations in a particular problem, you need to convert them into variances, because that's what this is. Okay, so now, I'll just write a little quick note. I kind of said this, but I want to actually write it down so that you guys have it in Word. So when we test the hypothesis that the two means are equal to each other, we're comparing means. Before, we made assumptions about whether or not the variances were equal to each other or not, okay? This testiness implies certain things, implies a relationship. Right, two distributions, I mean like X and Y. So remember, one of the relationships was that the variances were equal to each other, or that the variances were not equal to each other, right? We had a pooled test, we had a non-pooled test, we had to calculate all sorts of degrees of freedom and whatnot, okay, based on this. So it implies that, right, when we test this, right, we're making certain assumptions about it. But now we actually have a test that's going to tell us is which one of these is true. Are the two variances equal to each other, or are they not, statistically speaking? Okay, so so this test on variances should be done first. Or we test, oops, right, so that we know for sure, okay? I want to know for sure the variance is statistically equal to each other so that I can use case one. I can use a pooled variance. Or I want to know for sure that the variances are not statistically equal to each other so that I can use the non-pooled variance, okay, when I check this out.
So instead of it being told to us in the problem, then we can use the F-test to find it out for ourselves, is what you're
Right, exactly. Yeah. So like some of the problems, like obviously if they're from like, earlier chapters, we're going to tell you, we're going to say, assume the variances are equal, or I think some of the homework problems will say, use the pooled variance, right? And so the use the pooled variance implies that the variances are equal to each other. You'll see that in some of the earlier like the problems, I think in like chapter 9.2, they'll tell you which one to think about. But now as we move on into, I think 9.3 is like, we're just basically, we're testing variances, but like imagine we're going to go back and revisit some of the examples that we did before, like yesterday, and then we're going to see, well, instead of making this assumption, let's check to see if the variances actually are equal to each other, and were our assumptions okay? Okay, but yes, you're right. In reality, in real life, like you would have like two populations, you'd need to check their variances first, right, to see if the variances are equal. So then you'd know when you make this comparison of the means, right, are you doing it correctly, right? Because you're making certain assumptions about the underlying data. And so now we actually want to be able to find it first, okay? Are the variances equal, are the variances not equal, okay? Remember the chi-squared test that we did was actually a test of a sample variance to its population variance. This is variance of one population to a variance of another population. So it's two separate things, okay? Even though the F-test itself is based on the chi-squared, we're going to talk about that in a minute. Okay, we're going to actually come up with the F-test test statistics. You can see where all these things come from, okay? That answer your question?
Yeah.
All right, you guys will have this thing in turn the page. All right, so let's talk about the F-test. The F-test itself is a way to measure variability. Looks like I'm repeating the words, but I'm looking for the differences in variance. Okay, the variability of this variable right here. Okay, so let's remember, right? We've got these random variables. So for my X population, my X random variable, X1, X2, so on and so forth, all the way up to say N, right? So I've got a random variable of size N, right? I've pulled N people, N number of people, and I've got a given mean, and I've got some kind of a variance. Okay. If it's a whole population, you know, I would use sigma. If it's a sample population, I would use lowercase s, right? And we're going to assume that this is normally distributed. Okay. Because most things in nature are actually normally distributed. Remember, we talked about the law of large numbers on our binomial experiment. Okay, most things sift into a normal distribution. Okay, there are certain things like radioactive decay, radioactive particles come out in a different type of, I think they're Poisson. Okay, so but you know, if things don't work out right in a normal distribution, then you can try other distributions to see like what would fit. But most likely when you're doing some kind of an experiment, it's safe to say things are normally distributed. Because I've got X as a random variable, I'm going to do Y as a random variable. So this is Y1, Y2, all the way up to Y sub M. Okay, so this is a random variable. Size M. Now this was size N. This has mean. And it has a variance. That's a Y. And we're going to assume it's normally distributed. Okay, for our variables. Okay, so each of these variances, right, has a chi-squared distribution. And when we compare the sample variances to its population variance, so let's write that down. I'm going to do sample variance. Remember our chi-squared test statistic, right, which was a ratio, okay, and we had to make it an unbiased estimator, and we have n-1 s sub y squared over sigma y squared. Okay, so these are the chi-squared statistics for my x variable. This is my chi-squared statistic for my y variable. Okay, with n-1 and m-1 degrees of freedom. Okay, so these are the chi-squares. Okay, now our F statistic, or F test, sorry, is a ratio of our chi-squareds from my x random variable to my y random variable. Talk about some rules of thumb. How do I know? Do I put the x on the top or the y on the top? We're going to talk about that. Ratio of our chi-squareds. Okay, so I'm going to say my F. Let's write out the whole thing, okay? And then we'll simplify it. So this is n-1 squared, sigma squared. And I have to make this an unbiased estimator. Okay, so all these things cancel out, right? These cancel here. And this ends up being, let's group these together. So this is y squared times sigma x squared. Sorry, this is a y. Y squared. X squared. This is a y. Okay, so now this right here, our null hypothesis says that there's no difference between these two. Null hypothesis states sigma x squared equals sigma y squared, which means their ratio is equal to 1. Okay, so then this whole thing goes away, it becomes 1. So my F statistic essentially is a ratio, right, of my two sample variances. Let me write that down. I have the book here because I want to be able to show you the table, but it's really heavy. Let me move that out of the way. Okay, so our F test statistic looks like this. Okay. This is the thing you want to remember when you do your F test. Okay, it's like we said, I'm putting x in the numerator and y in the denominator. We're going to talk about some rules of thumb about how do I choose. It doesn't have to be x in the numerator, but I just have it written here like that, right? Because we're looking for a ratio of these two. Okay? But we'll talk about how do we know which one to put there in just a second. Let me know if you guys all need a minute. Okay, I'm going to turn the page. So this comes from our F table. This is our A.4 table in our book. Our book has a whole bunch of tables in its appendix. And this is dealing with an M and N degrees of freedom in a probability, like our alpha probability that we need to calculate. So when we draw this out, it looks like, I'm going to really exaggerate this. Okay. This thing is kind of like our chi-squared test in that it's what we call positively skewed, okay, which means that it has a really long tail on the right-hand side. Okay, so this thing here is our area equal to 1 minus p. So this is alpha equals 1 minus p again. And this value here is our F value that's based on the probability and our degrees of freedom, M and N. So there are 3 letters here underneath our F. Okay, one for the probability, which is related to our alpha, M and N. And if we have, this is for a one-tailed test. If we have 2-tailed tests, it's going to look a little bit different. We're going to go through examples so you'll see. Okay, so some notes about this, some rules of thumb. There. Okay, so the larger variance should be placed in the numerator. Right, when I said I wrote out the F statistic, I wrote S sub X all over S sub Y, okay? And I kind of did that. I said you can choose whichever, well, whichever one is the larger number you're going to put in the numerator, okay? It's a positively skewed, so we're looking for things, the larger numbers, okay, so regardless of subscripts. Okay, we're just looking for a ratio of these values. So if Y happens to be bigger, the sample variance for Y goes in the numerator, the sample variance for X goes in the denominator. For 2-tailed tests, again, our alpha value is divided by 2. And our critical value is placed on the right-hand side of the F curve. Okay, that's like saying this is the more important critical value after we divide alpha by 2. But what's going to happen is we're going to handle it like we did with our chi-squared test, where we have multiple pieces here. We're going to be able to look it up, and we're going to talk about how we actually calculate out these different values of our F, okay, to get our critical value, to find the critical regions on our F distribution. The standard deviation is given, which we'll do that, we'll trick you, or if your standard deviation is given, then this must be squared. Before using the F test. Okay, so if you're given standard deviation, be careful, right? Because we're going to try to trick you on that. We're going to see if you remember. It's a measure of variance. Okay, so we're just given standard deviation, square it, and then divide it out. And our degrees of freedom can't be found for whatever reason. Okay, you want to just find the closest value that's smaller, closest value on the smaller side. We're going to be conservative. Smaller numbers are going to give us a more conservative estimate of our F test. So we're going to choose the smaller numbers on the smaller side should be used. Okay. Pull this up. Okay. So some notes, some things that you need to think about how you need to do stuff. We're going to handle this, a lot of stuff in our examples, okay, but just to kind of have it out there as a rule of thumb. So let's talk about our characteristics of the F distribution. Okay. So we've got this curve, right? Our values, it's a ratio of variances. Variances are inherently positive, right? If you have a variance that's negative, maybe you've done a math calculation wrong, okay? Your variances are always positive. You can have a zero variance, which means it's a kind of a funny distribution, but you could have a zero variance, but always your variances are positive numbers, okay? So be careful. So our values of our F statistic cannot be negative, like our chi-squared, because our variance is always positive or zero. Zero is really unusual. You almost basically never get that. Okay. So the distribution is what we call positively skewed. We'll write that. We'll draw a picture. Distribution positively skewed, like our chi-squared. So it's like I've got most of my values here, and then I've got a really long tail on the right-hand side. Okay, negatively skewed, look the opposite. You have a long tail over here, and then it looks like this. Like the normal distribution is centered. Okay, it's symmetric. It's not skewed at all. All right, so the mean of our F is about 1. Okay, on our mean value, right about here. 4. F distribution, like the chi-squared, is a family of curves. So curves, and it's going to be based on our degrees of freedom and the probability. Okay, so like remember when we did our chi-squared test, we said it was a family of curves, right? So I'm going to have, it's going to look like this, or it's going to be shifted over, it's going to be big or spiky or whatever, but it's still basically the same basic shape. Okay, so it's a family of curves, but it's all based on our degrees of freedom. Okay. You guys good?
What does it say for number 3?
The mean of our F distribution is about 1. Right, so if I'm looking for the peak value, if I'm looking for that mean value, it's around 1 here.
Okay.
Yes, okay. Can I flip the page? Just some basic assumptions before we get into our examples. Some assumptions that we're making. The samples that we're getting are random. Right? My X1 is not related to my X2 in any way. Our populations are normally distributed. And the samples themselves are independent of one another. Okay, so some basic assumptions, same kind of assumptions that we've been working with so far, okay, in our normal distribution and our statistics portion, but it's important that we specify. And when you guys are all set, take out our lecture notes example page, and we'll start working through some stuff. Right, so on chapter 9.3, we're going to test the difference between two variances. So example 1 says, we're going to go back to that example that we did before yesterday, chapter 9.2, fastest speeds of male and female college students. And before, we weren't sure, like, are the variances the same? We kind of did a pooled. We said, oh, look, they're in the same order of magnitude. Well, let's test it now. Right now, we have some skills to be able to test to see if the variances are the same. So we're setting alpha equal 0.05. Okay, so we've got all of our data, same as before, and we're going to set up the same type of stuff that we did. So what's our hypothesis? Remember, we're testing variances now, okay? So our hypothesis is going to look like my null hypothesis that the two variances from the two different populations are equal to each other. My alternative hypothesis is that they're not, okay? Assuming that the variances are equal. Okay, so we're going to assume the variances are equal, but our alternative is that they're not equal, so we have to test that. Let's check it out. So our test statistic, okay, so my test statistic is our ratio of the F values. In this case, I'm the bigger one, right? In this case, S sub X is bigger, so I'm going to use that one, so 20.1. These are standard deviations, so I have to square them. Okay, so I'm going to do that. And when I do that, I square them out and divide it out, I get 2.714. That's my test statistic. Okay. All right, now I need to figure out my critical value.
Do you always pick the one that's going to be greater to put on the top?
Yes, it's positively skewed, so you want to do that.
Okay.
Okay, so our critical value. So not equal means this is a two-tailed test, which means I have to divide my alpha by 2. So 0.05 divided by 2 is 0.025. Okay, keep that in mind. Now let's take a look at our degrees of freedom. Okay, so I've got n equals 34, m equals 29. Okay, so I've got m equals 34 n equals 34 minus 1, which is 33, and my m is 29 minus 1, which is 28. So I've got 33 and 28. Okay, and we're going to talk about, I'm going to open up the book and I'll show you like how I'm reading these things, but let's draw out this picture here. So here's my F curve. I'm going to exaggerate it because it looks like that. So now I've got 0.025 is the area here, and then here 0.025 is the area there. Okay, so I'm looking for my F values that are going to delineate, right, this part of my critical region and this part of my critical region. For that, I need to look it up in the book. Let me get out my book here. So what happens is, I'm going to look at my book here. So this is, so on my book, it starts on page 682, but it says percentiles of F distributions, if you guys can see that. Percentiles of F distributions, you can see how it's set up. Good. All right, this is one of my degrees of freedom. M is my other degree of freedom across the top. P value, that's the probability that I'm calculating. That's my alpha or my 1 minus alpha, okay, to calculate those values. So let's think about it before I actually look at my P values. So the F values that I need to look up are, okay, I have to calculate 2. So one of them is going to be 0.025 for this end, right? And I want to do 33 and 28. The other one is going to be F. I have to subtract. I have to go this area, so I want to go, this P value is 1 minus alpha equals P. So my P value here is going to be 0.975, and my degrees of freedom are the same because I've got two ends of my critical region. Even though the area is equal to that, the P value, I look up the P value over here and I look up the alpha value over here, kind of like what we did with the chi-squared test. Okay, so these are the metrics that I'm looking up. 0.025, 33.28, 0.975, 33.28. All right, let's look at our table here. So
does it matter which you label M and which you label N? No,
because look, I'm looking at it goes this way and I'm going that way. It's typically like the numerator and the denominator, you know, it's typically kind of how you're thinking about it, but it doesn't, you're still going to get the same value.
Okay.
But it's the P and the alpha that are really important. You want to make sure you don't mess that part up. All right, so let's take a look. Oh, I'm going to cruise along. So I need to find one that says 33 and 28. So I'm going to keep going. And I'm looking over here and still 20. Oops. And I go, so I go 15, 20, 24, 30, 40, 60. All right, so I'm like, how do I do this? So 33 is close to 30. And then look at what's happening here on the M part of my table. 24, 12, 15, 20, 24. This is the same thing, right? So these are the same values that we just saw on the N part. So because I don't have 33 and 28 specifically for my N and my M, I'm going to use the degrees of freedom that are closest. Remember how they said if you can't find the degrees of freedom, find the one that's like closest to it, but on the smaller side. So I'm going to choose 30. And on the other side, I'm actually going to
the floor of it, or if it's like 38, are we going to round up to 40?
you're gonna use your judgment, right? You're not gonna do the floor. So if it's 38, I'm gonna round up to 40. Like we're gonna do this right now. So 33, 33 is closer to 30 than it is to 40. 28 is closer to 30, right? And so I'm gonna use, than it is even to 24. So I'm gonna use 30 and 30 as my 2 degrees of freedom. Okay, so let me write this down. This is actually, I'm gonna use 30 and 30. And this is 30 and 30 from the table, 0.025, 0.975. Okay, oops, sorry. Okay, use your judgment, but spell it out, right? Which one that you're choosing. Always when you're doing this stuff, spell out like what your assumptions are and which ones you're actually using. So, you know, I mean, like we're in a class, so I'm going to be grading you. Like if you choose like 50 and 60, it's like kind of like, why did you do that? But, you know, if you're in a job, you also want to state what your assumptions are, right? You're writing up a paper, you're writing up a proposal. You want to state this exactly so that other people can go check, right? So that they can understand your logic for how you got certain things, okay? They can challenge it or support it, basically, based on that. So let's do this. So I'm going to choose 30 for my N, and I'm going to choose 30, oops, sorry, 30 for my M. And my p-values, I'm going to do 0.025 and 0.975. Okay, so you see how I have to, I'm looking on the right column. I'm already in the right row area. And I choose the p-value for the left-hand portion and the p-value for the right-hand portion. And these values that are listed here, 2.07 and 0.482, correspond to my F critical values, okay, that are going to be on each of the tails of my distribution here. So this one here, 0.025 is equal to 0.482. This one for 0.975 is equal to 2.07. Okay, these are my critical values. This goes 0.482. This is 2.07. Everybody see how we read the table? You can see why I didn't photocopy it. It's like pages and pages and pages long. Okay. All right, but I encourage you to take a look at that from your book. Okay. So now we have our critical values. Okay, we have our test statistic. Now we need to make our decision based on where things are at. So 2.714. So you can see, let's write down our decision. So our test statistic, which is 2.714, is greater than our critical value, our positive critical value, which is 2.07. Therefore, right, it puts us like right here. This is our test statistic, okay? Therefore, we're going to be able to reject the null hypothesis. Remember, our null hypothesis said that the variances were equal. Now we know the variances are not. So when I go back and I look at comparing the means, I need to use a test that does not pull the variances together. I'm going to use a test that assumes that these variances are different than each other. Okay, so this means that variances are not equal at the alpha 0.05 level. It's statistically speaking, right? Which means that the test we did in the previous chapter, which assumed that the variances were equal, we did a 2-sample t-test. We're going to say that that was not valid. We need to go back and do it again. Okay, so I'm going to make that conclusion. Therefore, I'm going to use the 2-sample t-test, okay, that has different variances, not the pooled. Okay, and then we have to calculate out that we could use t-test or a z-test with different variances. Okay, it means I have to calculate out my degrees of freedom differently and all that. Okay, everybody see how we did all that. Before I move on to the next example. Anybody need more time to write before I flip the page?
I'm good with it.
Okay. Right. Okay, so example 2, let's talk about. Example 2 says, we're at some given airport, right? And we're looking at the hypothesis is that the variance for the number of passengers for American airports is greater than the variance for the number of passengers for foreign airports. I think they mean like destinations, right? So I'm at a given airport and I'm traveling to an I'm traveling domestically versus I'm traveling to outside the country. We've got an alpha 0.1, okay? So our alpha 0.1 level, we want to know if there's enough evidence for this difference, you know, the difference in the variance. We're going to use the p-value method, so you can see how we would use the p-value method for our variance test. Okay, we're going to assume the variables are normally distributed. The data is in millions of passengers per year. So this right here is our boundary line between the two. It's hard to get that table to work this right. Okay, so American airports, these two columns, non-American foreign airports, those two columns. Okay, so let's state our hypothesis like we have been doing. Oops, let me give myself room. My null hypothesis is that the two variances are equal to each other versus my alternate hypothesis, which is they said that there's more, so the number of passengers is greater than, right? So this is a one-tailed test. Okay, so greater than, instead of being, are they different, we're saying, are they greater than, right? So this is why we have a one-tailed test right here. This is our claim. Okay. All right. So we need to calculate our test statistic. Okay, for this, I have to calculate a bunch of stuff. Like I've got to calculate the variances and stuff. The first thing I'm going to do is I'm going to compute the variances. Remember, your calculator will actually do that for you. If you need help with the calculator stat function, come see me in office hours and we'll work it out. So you need to compute the variances. So offline, I did it. We can call this our X and our Y. This is 95.87. Okay, so my variance for one population, my variance for another population, right? And now I have to calculate my F statistic, my F test. So my F test is going to be, I'm going to look for the bigger one of the two. So I'm going to go sigma X squared over sigma Y squared. So I'm going to put 246.38 over 95.87. These are variances, remember, not standard deviations. And I'm going to get a test statistic of 2.57.
So we always make the bigger value our X.
Numerator. You make the bigger value your numerator. The bigger, I mean, this could have had a bigger value, and I would have called it Y, but I put the bigger value in the numerator.
Okay.
Yeah. Okay. Find our critical value. Let's draw a picture because this is a one-tailed, right? So we need to also find the p-value, which is really what we're doing here. Find our p-value. So I'm going to draw a picture. Goes like this, right? This is a one-tailed test, right? So we're looking at, right, our alpha equals 0.1. Okay, so remember we have to calculate our p-value, right, based on that. So we'll do this all over here. So I've got and I've got have to count 1, 2, 3, 4, 5, 6. So I've got 6 data points in my X distribution. My M equals 4. Okay, so I'm going to use this to calculate degrees of freedom equals 5. My degrees of freedom equals 3. Okay, so I'm going to sum up these to help me figure out my degrees of freedom. So since my alpha equals 0.1, okay, my alpha equals 1 minus p. Okay, so then my p-value is equal to 0.9. Okay, this is a p-value that I need to think about. So then my F statistic, just so that you know, I'll write it in purple. So my based on my table and the degrees of freedom, 0.9, 5, and 3, my F statistic is 3.62. I'll put that in parentheses because we're not comparing F values, we're doing probabilities here. Okay. So I've got this p-value. Now I have to figure out given my test statistic, which was 2.57, I have to like reverse engineer my 2.57 to find out what like kind of p-value that would be associated with. So that gives a p-value with these degrees of freedom. Okay, that's a p-value between 0.75 and 0.9. Okay.
So if it was left-tailed, would our p-value be 0.1?
It would be smaller, yeah. Well, you would use alpha at that point, and then you would be looking for you'd be comparing the alpha, right? And so then I would still be comparing this value. If it was a left-tailed test, this value would probably be smaller, and I would be over here, right? And I'd be looking for p-values that are smaller than that.
Mm-hmm.
Okay. So I'm gonna write this. This, by the way, I'll write this in purple. So this is associated with an F of 1.88, and this is associated with an F of 3.6. Okay, but let's write this out. Okay, so we would say 0.75 less than our p-value, which is less than 0.9. Okay, so this is our basically like our critical value. Now I need to or what we get from our test statistic. I'm sorry, this is like our test statistic. Okay. And I have to compare that with my alpha, my p-value. All right, so our decision, our p-value, which is 0.75, is greater than our alpha, we specified at 0.1. Okay, so therefore, we're not going to reject our null hypothesis. Okay, in terms of areas, right, what we're looking at is like this, right? We found p-values 0.75 to 0.9. So I'm going to draw this out as right. So my area under the curve is like between 0.75 and 0.9. My alpha is equal to 0.1. So you can see how our p-value is like way bigger than our alpha value, right? You want your p-value to be able to reject the null hypothesis. You want your p-value to be smaller than the area that you're comparing it to. Okay? So we're not going to reject the null hypothesis, which means in words, there's not enough evidence to support the claim that American airports have greater variance than foreign airports. So now when we go to do a test on the means of these two, I can say we're going to do a pooled test because the variance, statistically speaking, the variance are not different. Okay, so I can use a pooled variance test, which makes my statistics a little easier. Okay. Anybody need more time to write? Okay. I'm going to turn the page. All right, our last example. Okay. This one says we're going to use EEG recordings. EEG recordings, some of you guys have heard of EEG recordings, just like electrodes that measure electrical waves in your brains. Okay, they put like, it's non-invasive. They just kind of put little stickers like this kind of helmet, like this loose swim cap over your head, and they put these like stickers on your head that have like electrical receptors that measure it. They don't go into your head at all, but it basically measures, okay, the brainwave activity, okay, based on electrical recordings. So there are two groups, okay, 10 subjects each. The question is this, is the difference in variability of alpha waves. So alpha is a particular frequency, right? So you have like 10.7 cycles of your alpha wave per second, say for example, 10.7 hertz, okay? So alpha waves are within a given range. We have alpha, theta, all sorts of different waves, and they're all required for things like learning and memory and stuff in your brain. So this is alpha waves. So we're going to variability of alpha waves statistically significant at the alpha, which is a different alpha. This is our significance level at 0.05. Okay, so let's go ahead and tackle it. We're going to have to do some prefetching on things like what's the variance of these different populations, but we can do that. So our hypothesis is, our null hypothesis is that the variances are equal versus our alternative hypothesis. This is two-tailed because they just said, is there a difference? They didn't say is one greater than the other, is one less than the other. They said, are they different? Okay, so it's a two-tailed test. Okay. So to calculate out our test statistic, okay, let's do this. This is, we have to first calculate our sample variances. Okay, so when we calculate these out, what did I get? I got squared is equal to 0.21. Y squared is equal to 0.36. Okay. All right, so we calculated our variances, and I'm going to calculate out my F statistic. All right, I'm going to look at which one's bigger, SY, 0.36, 0.21, okay, which is going to give me 1.71, and my N equals my M, which is 10. Okay, we've got 10 samples in each, so N equals M equals 10. Our critical value is going to come from the table. And remember, this is a two-tailed test. Like that. Really exaggerating. Oops, sorry, you can't even see what I'm doing. I'm really exaggerating these areas here. There. So this is my, it's two-tailed, so alpha over 2, 0.05 over 2, 0.025. So the area under here is 0.025. The area under here is 0.025. Okay. I look up F sub alpha on this side. Okay. But I'm going to look up 0.025, and I can look up, remember our degrees of freedom are 1 less, so 9, 9. And then I'm going to look up my p-value. This is 1 minus that, 0.97599. These are my degrees of freedom. Okay, so these come from the table. I'm looking things up. For 0.025, I got 0.248, and for 0.975, I got 4.0. Okay, so this is 0.248, and this is 4.03. Okay, on either side. So that gives you my F value that defines my critical region. Okay, we're going to compare it to this thing, our test statistic. Our test statistic ended up like right about there, 1.71. Let's see where this decision is going to go, right? So the decision, we're going to say our test statistic, which was 1.71, is greater than our lower end of our critical value, 0.248, but less than our other critical value of 4.03. Okay, so it's within this non-critical region. Okay, so therefore, I'm not going to reject the null hypothesis. Okay, so based on our evidence, there's not enough to say that there's variability. Okay, so let's write that out. So there's not enough evidence to conclude that the variances are different. Which means when I go to do a test on the means of these two populations, I can do a pooled test. Okay, a pooled variance. I'm going to say the variances, statistically speaking, I did the F-test. The variances, statistically speaking, came out to be not different, which means now I can pool, right? Pool their variances, and then I can calculate my test statistic on my t-test using a pooled variance. Okay, when I go to check out the differences in the means. Okay, so technically speaking, we probably should have done this chapter first, but I think it's easier to think about when I'm comparing two populations, to think about comparing the means first, and then to think about, well, how we're going to compare things with the variances. Okay, but this is a test that you would want to do first. Okay, unless you're told otherwise. Like in the book, like I said in chapter 9.2, you're told use the pooled variances. Variances are equal, variances are not equal. So you get a feeling for what kind of test you need to do because you're being told to, right? But in reality, okay, you would need to do some kind of a test on the variances first to find out what kind of a t-test you need to do. Okay. And that's basically it for chapter 9.3. Okay. This is not on the test. Okay. It's not on our homework, but it will be due next week. Okay. So keep that in mind. Okay, guys. So what I'll do right now is I will